This question asks you to identify the correct statements about the orthogonal matching pursuit (OMP) algorithm in scikit-learn, a popular Python library for machine learning. We'll look at several statements about OMP and decide if they're true or false. This describes the input data. Imagine a spreadsheet, 100 rows and 50 columns. Each row represents a data point, and each column represents a feature. This is what OMP uses to build the model. This is what we want to predict. Think of this as a single column in a spreadsheet with 100 values. The goal of OMP is to use the design matrix to accurately predict these 100 values. The parameter _non_non_cofs in OMP sets a asterisk limit on the number of non-zero coefficients in the solution, not a guarantee. It's like saying, I want at most 10 ingredients in my recipe, but you might end up using fewer if you can achieve a good result with less. This statement is correct. OMP works step by step. It looks at each column, called an atom, in the design matrix and picks the one that's most helpful in improving the prediction at each step. This is false. The time it takes OMP to run isn't just based on the number of rows, data points. The number of columns, features, and how sparse we want the result to be, the value of (n_non_0_cofs) also matter a lot. Incorrect. While increasing this parameter can improve accuracy, it's not guaranteed. Adding too many non-zero coefficients can lead to overfitting, where we get good results for our training data but poor results with new data. Think of it like adding too many ingredients to a cake recipe. It might not make it better. This is the specific algorithm we're dealing with. It's a clever way to find a concise representation of data, ideal when you only want a few key factors. This refers to the overall process. The final aim is a compact model using only a few of the available features to represent data points effectively. I'm using the scikit-learn library, specifically its orthogonal matching pursuit (OMP) function, to solve a problem. OMP is a powerful algorithm for finding sparse solutions, meaning solutions with only a few non-zero values. It's great for situations where we want to extract the most important features from a large dataset. Think of it like finding the key ingredients in a recipe. We only need a few to make a great dish. I have a multiple-choice question to test my understanding of how OMP works and its behavior within scikit-learn. I'll be analyzing different statements about OMP to identify the true ones. I'm working with a dataset. My design matrix, X, has 100 rows, samples, and 50 columns, features. My target signal, Y, represents 100 individual measurements or observations that we are trying to predict. I'm going to use OMP to find a sparse representation of Y using the features in X. The result of my analysis will be to determine which statements about the scikit-learn's OMP algorithm are correct. I'll be evaluating the algorithm's behavior, its complexity, and the meaning of parameters in a methodical and rigorous way. I see, you're working with OMP, a powerful algorithm for finding sparse solutions. In simpler terms, it helps you find the most important features from a large set of data. Think of it as a detective trying to solve a mystery with limited clues. OMP effectively picks the most relevant clues to reveal the solution. This question tests your understanding of OMP's behavior when using scikit-learn's implementation. The goal is to see if you get the nuances of this algorithm. This statement hits the nail on the head. OMP works iteratively, meaning it goes step by step. In each step, it selects the column, atom, of the design matrix that is most strongly correlated with the remaining error. Imagine trying to build a tower using blocks. OMP takes the block best matching what you need at each stage. This is a crucial aspect of how OMP achieves sparsity. It focuses on the most influential elements. This is incorrect. The runtime doesn't scale linearly with the number of samples, rows in X. It's more complex than that, influenced by many factors like number of features and desired sparsity. It's more like polynomial scaling. It grows faster than linearly. Absolutely not. While increasing the number of allowed non-zero coefficients might lead to a lower MSE, it's not guaranteed. It can even lead to overfitting, a situation where your model performs well on the training data but poorly on new data. It's not a surefire way to improve accuracy. Think of it like this: adding too many ingredients to a recipe doesn't always mean a better dish. Nope, this is incorrect. The n underscore non-zero underscore cofs parameter in scikit-learn's OMP implementation only sets an asterisk upper limit on the number of non-zero coefficients. It doesn't force the algorithm to use exactly that many. OMP might stop earlier if the remaining error is already small enough. This tells us the size of your data matrix X. There are 100 data points, samples or rows, and each data point is represented by 50 features, variables or columns. This is your target variable, of length 100. You're trying to reconstruct this signal or predict this value using a linear combination of columns from X. This is the algorithm you're using to solve the problem of reconstructing the target signal from the design matrix. This algorithm has the key properties of sparsity and iterative selection of features. The ultimate aim of using OMP is to get a sparse representation of the target signal. It means reconstructing it using as few features as possible, making it easier to understand and interpret. I'm using scikit-learn's OMP, a powerful tool for finding sparse solutions to problems. It's like a detective trying to solve a mystery with the fewest clues possible. It's all about finding the most important pieces of information. OMP helps reconstruct signals in a way that uses only the essential elements. We are assessing the truthfulness of statements about how OMP works in the scikit-learn library. I have a design matrix, X, which is a 100 by 50 array. Think of this as containing 50 potential ingredients, features, for 100 different recipes, samples. Each entry indicates how much of each ingredient is in a given recipe. And I have a target signal, Y, represented by a 100-element array. It's the overall flavor profile for each of the 100 recipes, which I want to reconstruct. My goal is to use the ingredients, X, to approximate this overall taste, Y. I'll use the OMP algorithm to achieve this approximation. My aim is to get a sparse representation of Y, that is, finding a solution with few non-zero coefficients. It's like finding the fewest essential ingredients to approximate the taste. The fewer ingredients, the simpler and more efficient the recipe. I'm using scikit-learn's orthogonal matching pursuit, OMP, a powerful tool for finding sparse solutions in linear regression problems. It's like finding the simplest explanation possible using the fewest key ingredients. This is a multiple-choice question testing your understanding of how OMP works and its behavior in scikit-learn. This statement is correct. Think of it like this. OMP starts with the signal you're trying to reconstruct and looks at all the atoms, columns of the design matrix. At each step, it picks the atom most similar to the signal it hasn't explained yet, the residual. It keeps adding atoms until it gets close enough or hits a limit of atoms. That's pretty cool, right? This sets the stage. I've got a signal, Y, a set of building blocks, X, and I want to build Y using as few blocks as possible. X is a 100 by 50 matrix, meaning 100 data points made up of 50 features. I'm trying to fit my signal with at most 10 of these features to keep things simple. This is false. The runtime isn't just about the number of samples, rows. It also depends heavily on the number of features, columns, and the desired sparsity level, the number of atoms used. It is more of a polynomial complexity. That's also incorrect. While adding more atoms can improve the fit, reduce MSE, it isn't guaranteed. Overfitting can happen. You might match the noise and not the signal. This statement is false. The n underscore non-zero underscore cofs parameter in scikit-learn's OMP sets an upper limit, not an exact number, of non-zero coefficients in the solution. OMP might stop earlier if the approximation is already sufficiently good. I'm using scikit-learn's orthogonal matching pursuit, OMP, a powerful algorithm for finding sparse solutions to problems. Think of it as a clever way to find the most important bits of information in a large dataset by focusing only on a few key factors. OMP is particularly useful when dealing with signals, like sound or images, that are mostly zeros with just a few important non-zero values. We're tackling a multiple-choice question that tests how well you understand OMP and how it works. I have a problem where I'm trying to reconstruct a signal, Y, using a technique called orthogonal matching pursuit. I have a matrix X which represents my data, and my goal is to find the most important parts of this data to represent the signal in a simplified way. I want only at most 10 non-zero values. This statement is correct. OMP works by repeatedly selecting the column in my matrix X that's most closely related to the part of the signal that I haven't explained yet, called the residual. It's like building a puzzle. I keep adding the most relevant pieces to fit the whole image. This is incorrect. The time OMP takes isn't just determined by the number of samples. It's also affected by the number of features, columns in X, and how sparse the solution needs to be. This is incorrect. While increasing the number of allowed non-zero values might reduce the error, it's not guaranteed. It can lead to overfitting, where I'm fitting to the noise in my data, rather than to the actual important parts of the signal. The design matrix X is a 100 by 50 matrix. Each row represents a data point, and each column represents a feature. I use it to represent all of the information I have available in order to reconstruct the signal. The target signal Y is what I want to approximate or reconstruct using OMP and the features from my matrix X. It's a vector of length 100. This is the core algorithm I'm using. It iteratively selects the most important features to obtain a sparse representation of the signal. My goal is to find a simplified, or sparse, representation of the signal Y using only a small number of non-zero coefficients to capture the essential information. I'm using OMP, a technique from sklearn, to reconstruct a sparse signal. It's a powerful tool for finding a small set of important features from lots of data. Think of it like finding the key ingredients in a complex recipe. Instead of all the ingredients, OMP helps you identify the crucial ones. This question tests your understanding of how OMP works and behaves in practice, within sklearn. I'll look at several statements about OMP and decide if they are true or false. We'll need to think carefully about what each claim means. The design matrix X is our data. It has 100 rows, samples or observations, and 50 columns, features or variables. Think of each column as representing a different atom or basic building block to reconstruct our target signal. This is what I want to reconstruct using the data in X. It's a signal with 100 values, matching the number of samples in the design matrix. My goal is to find a sparse representation, that is using only a few of the 50 columns in X to accurately model Y. This parameter controls how many non-zero coefficients I allow in my solution. I'm aiming for sparsity, hence a solution with at most 10 non-zero coefficients. This limits the number of features used to reconstruct my signal. It sets a limit, but the algorithm may not always achieve it. This is the algorithm I'm using. It's an iterative process. In each step it picks the feature most correlated with what's left to be explained. It tries to do so in the most efficient way using orthogonal projections. It aims to find the sparsest possible solution, a way of representing my signal that uses only the most important pieces. Increasing the number of allowed non-zero coefficients, NNONZEROCOEFS, might improve the reconstruction in some cases by making my model more complex, but may also lead to overfitting and worse performance, especially if the underlying signal is actually sparse. It doesn't guarantee a lower error. The time OMP takes isn't simply proportional to the number of samples. It's affected by the number of features and the desired sparsity level. The relationship is more complex, not simply linear. OMP works by repeatedly choosing the feature that best explains the remaining signal. That is, at each step, it selects the feature, column of X, with the highest correlation with the part of the signal I haven't yet explained. The parameter NNONZEROCOEFS sets an upper limit, not a guarantee. It's the maximum number of non-zero coefficients. OMP might stop sooner if the reconstruction is already good enough.